right, this is going to be our very last lecture for the year. And this last lecture, we are just learning new terminology. We're not going to learn new procedures. We're going to do an old procedure, but we're going to learn what it means in a different application. Okay, so we are going back to vectors. Okay, so remember a vector is a quantity that has both magnitude and direction. And the way we're going to study vectors, we're going to use them in their component forms in this lesson. Okay, so one of the things that we've done in the past is that we took two vectors and we multiplied them together. And we did that with what was called a dot product or a scalar product. Today, we're going to take two vectors and we're going to multiply them together in a different way. And the answer is going to be another vector. Okay? All right, so just to refresh your memories, right here I have the dot product. And so I have two vectors, vector A and vector B, and I've just given them generic components. I have given them three components. Remember, vectors can have any number of components, but these are two three-dimensional vectors. And that's just because it's easier to do dot product. Well, it's not easier, but dot product with three components. Okay. Or cross product. Okay, so but here's the dot product. The way you do the dot product is you take the first components, you multiply them together, and then you take the second components and multiply those together, and then you take the third components and multiply those together. And then your final result of the dot product is adding those three things together. And when we just went over matrices and we learned matrix multiplication, we learned that in matrix multiplication, you do rows of the first matrix, dot columns of the second matrix, and that's how you get your new entries. All right, so that's what we did previously. And notice that what you get is a scalar. You don't get a vector. You just get three numbers added together, which is just one number. So you just get a scalar equals scalar. All right, so today, and vector products, it's also called cross product, and that is simply because instead of using a dot between the two matrices or the two vectors, we put a cross for the times, so for the multiplication. So you use a cross there. So now the way that we do the cross product is we actually just determine the determinant of a 3 by 3 matrix. In this 3 by 3 matrix, so we create this matrix from the two vectors, and in our first row, we put our three unit vectors, I, J, K. Remember, I is the X direction, J is the Y direction, and K is the Z direction. And so numbers in front of, so for example, when I write vector A as A1, A2, A3, writing it in component form with our pointy brackets is this is how you write it. But you can also write the components in unit vector form by saying A1 in the I direction, A2 in the J direction, and A3 in the K direction. And so our answer to our cross product is going to be in this form. All right, but you can easily just switch between the two forms. It's just a matter of whether you use commas and pointy brackets or pluses and IJKs. Okay, so we're going to do a determinant, and you just learned how to do determinants. And so it's just another determinant where your first row are I, J, and K. Your second row is your first vector, and your third row is your second vector. In vector product, A cross B and B cross A are not the same. They're similar, and there's one thing that's different about them. They just point in opposite directions. But their components are the same, and they just point in opposite directions. Okay, so the best way to do this is just to get in there and do an example. And so here I have two three-dimensional vectors, A and B, and I'm going to find the cross product of them, or the vector product of them. So A cross B. And I'm just going to write down that definition that I had before. It's the determinant of, and now I'm going to put in a 3 by 3 matrix, but I'm not going to bother putting the square brackets. So the first row has the three entries I, J, and K. The second row is the vector A, and the third row is the vector B. Okay, and we're going to find the determinant. We're going to find the determinant of this matrix. All right, now the way that we do determinants is with minors and cofactors. So it's always best to just choose your first row to do the determinant along. And I'm going to start with I, and so I cancel the row and column I is in, and I am left with this 2 by 2 matrix here. So I'm going to write the determinant of 1031 times I. And now I'm going to move on to my second entry in the first row, the J, and I cancel its row and column, and I have left with the 2 by 2 matrix 2, 0, negative 1, 1, and I'll do the determinant of that times the J vector, and notice the J vector is in the negative spot on the checkerboard, and so I minus that. And then finally, I move on to the last entry in the first row, the K vector, or the K unit vector, and I cancel its row and column, and so I'm left with the 2 by 2 matrix 2, 1, negative 1, 3, and so I do the determinant of it, and I multiply that to the K unit vector. Okay, and then now I just have to do these 3 2 by 2s, which are simple to do the determinants of. So in the I direction, I have 1 minus 0, so that's 1I. And the J direction, I have 2 minus 0, so that's minus 2J. And then the K direction, I have 6 minus negative 1, so that's plus 8K. And here is my A cross B vector. So it's this vector in unit vector form, or in component form 1, negative 2, 8 is the answer there. Okay, and now on this last page, I'm just going to talk about geometrically what happens with these two vectors. What happens is you have two vectors. They are tail to tail, and when we do the vector product, okay, so let's say I have a vector A and a vector B, and I'm putting them tail to tail like this. And when I do the cross product of them, then if I do A cross B, say, then I get a vector that is pointing, and it's perpendicular to both A and B. So this is a three-dimensional drawing here. This is A cross B. And so it's a vector that's perpendicular to both of them, and it points in a specific direction. There are two possible vectors that are perpendicular to both A and B. One would be pointing, and so because A and B make a plane, so I'm kind of drawing a horizontal plane here with A and B, and then vector A cross B is pointing up towards the top, out of the plane. There's another vector here that would be pointing down, out of the plane. That's actually the answer when you do B cross A. And so the components will be the same, or the magnitudes will be the same, but they will point in opposite directions. Okay, so here's what the right-hand rule is. Here's how you determine which direction you point in. And this is really something that you have to see in person, so I'm going to do my best. But what you do is you're going to take your right hand, and you're going to point your fingers in the direction of your first vector. So that would be in the direction of A. And then you're going to put your palm, okay, the palm faces the direction of the second vector. So my fingers should be pointing here, and then my palm should be facing B. Okay, now the answer is to look at your thumb. If your palm is facing B, then your thumb is down. Oh, I did this backwards. A cross B points down. Look at that. Yeah, so if you do A cross B, then you get the one that points down. Look at that. And then if you do B cross A, you get the vector that points up. Okay? And that would be because now your hand is facing the other direction. Okay, this is also, by the way, righty-tighty, lefty-loosey. When you have a screwdriver, your thumb points in the direction that the screw is going. When you rotate your hand the way that I've described how you rotate it with a vector cross product. Okay, and then the final thing here are a couple of properties. When you have two vectors, A cross B, and the angle between them is phi, say, then the magnitude of the resulting vector is AB sine theta. So it's the magnitude of A, so this is magnitude of A, magnitude of B, times the sine of the angle between them. Now, remember in dot product, it was the same thing, except that was a cosine, not a sine. And this n vector, so it's times the unit vector pointing in the direction of the right-hand rule. So this makes it still a vector. But this is your magnitude of A cross B. If you take a vector and cross it with itself, then you get the zero vector. And if you, we already just talked about this one, that A cross B is the opposite direction of B cross A. And we are finished.